Hi guys. Okay, so in this video, we're going to be looking at the shapes of the molecules. First of all, what is the importance of shapes to the molecule? The shapes influence the physical and the chemical properties. For example, the melting points, the boiling points, the chemical reactivity, how the molecules react with each other. All that is dependent upon the shapes. Next, the real-world applications of understanding the shapes of the molecule lies in drug discovery. So in a very simple layman terms, I'll try to explain to you that in the body, there are receptor regions. In those receptor regions, there are target binding sites. And the new molecule that you have designed in the lab, that is called a drug ligand. So the shape of the drug ligand should match with the target binding site. So when this drug ligand goes in the body, and it should basically bind to the target in order to produce the desired therapeutic response. That is why it is very important for the drug candidate, that is the drug ligand, to have that exact shape that matches with the target site. Okay, so now let's look at how do we determine the shapes of the molecule. Okay, so here on the screen, as you can see, is a table that we use as a reference in determining the shapes of the molecules. So one thing very important is the central atom. What is happening around the central atom? That is critical in determining the shape. So how many lone pairs are there around the central atom? How many bonded atoms are there around the central atom? Okay, and what are the bond angles of the central atoms around the central atom? Okay, so all that influences the molecular shape and the electron geometry as well. But molecular shape is the shape you see from outside. This is in regards to the bonded atoms. Electron group geometry is internal. So this piece is more internal. Internal means how the shape is with regards to the electrons or the placement of the electrons. Now, there's something called electron groups. Now, electron groups are basically electron clouds, okay? So these are just electron clouds. In other words, lone pair is one type of cloud, single bond is one type of cloud, double bond is one type of cloud, triple bond is one type of cloud. So we just count these clouds. That's all we do. So for example, if there are two electron groups, this means that there are two atoms are bonded and there's no lone pair. Next is if there are three electron groups, this means that there are three bonded atoms and no lone pair. Then we have the another example of three electron groups, and those three electron groups, once again, two bonded atoms and one lone pair. So two bonded atoms and one lone pair combined together, that makes it three electron groups. Look at four electron groups. These are the four categories of electron groups. And that is just basically electron clouds, okay? So there are four bonded atoms and zero lone pair. Or there could be three bonded atoms and one lone pair, and two bonded atoms and two lone pairs. Now, what are lone pairs? Lone pairs are non-bonded electrons, means that they are not forming any bond. They're just two little dots sitting on top of an atom, as we show, and those are, not bonded. So based on the arrangement of the bonded atoms and the electron clouds of coming from the lone pairs, these two sets are going to influence the angles also. At what angles they are, towards each other. So based on that, there are shapes, and we're going to look at the shapes in a minute. But just an example here of the different steps that I talked about. First is always look at the central atom. Now I'm going to use a different pen here. So central atom, first look at the central atom, which means that it's very important you know what the Lewis structure is. Next is on the central atom, look at the lone pair, look at the bonded atoms. If you see them, then you come back to this table and all you need to do is just match them with the molecular shape. Molecular shape for mostly, for Chem, 30A and Chem 007, introductory chemistry courses. But once you go to a higher level, then we start talking about electron group geometry also, because that plays an important role in hybridization. So hold on to that one now. So here we are going to look at now the examples. So for example, BF3. So how does BF3 look like? So boron trifluoride. So here is boron trifluoride. So this is the Lewis structure. And in this Lewis structure, we see boron and fluorine and all these different angles. So now you have to look at boron and you have to ask yourself two questions. Does it have lone pair? How many bonded atoms does it have? It has got 3 bonded atoms, which are fluorine, and 0 lone pair. So LP is, I'm going to just put it here, BA stands for bonded atoms, and LP stands for lone pairs. Okay, so you go back to your table and you see whether, this 3 and 0 matches. So we see that 3 and 0 match to the trigonal planar. Okay, so trigonal planar is this piece right here, trigonal planar. Okay, so here is the shape of BF3 as trigonal planar, and that's all we need to write. The answer as trigonal planar. And now, how does it look like in a trigonal planar format? I'm going to show you in a 3D modeling. Okay, so hold on to it for a minute. Next is carbon tetrachloride. So carbon tetrachloride, how does it look like? It looks like this: 3 chlorines in a tetrahedral fashion. That's carbon in the middle and connected like as if they are in a chair. Sorry, let me just do it cleanly. See, chlorine here on top, and this is chlorine, this is chlorine, and this is chlorine. Okay, so we have here 4 chlorine atoms and no lone pair on the Lewis structure. So 0 lone pair and 4 bonded atoms. So what does this relate to? You go back to the table and you see that 0 lone pairs and 4 is right here, 4 bonded atoms and 0 lone pairs, and it's 109-degree angle. So that shape is tetrahedral. And what does it look like? Somewhat the way I have drawn, but really this is more like a chair. So imagine carbon is in the center, one leg of the chair is at the back, that is where the chlorine is, one leg of the chair is in front, so this is where this chlorine, and one of them is on the side and one is on the top. So the one that is on the side is, or at the back, is more like a wedge, like this like like a broken line. Okay, and so like a 3-legged chair. So this is how it looks like, and the angle in between carbon, between the carbon and chlorine and the other carbon and chlorine is 109 degrees. So we'll show you again in a 3D modeling in a minute, but just write down the shape. The shape is tetrahedral. This shape, this is how it looks like. Okay, next is the ammonia. So how does ammonia look like? And ammonia is N, 2 dots on top, and the 3 hydrogens here at the base. Okay, so this is the Lewis structure of ammonia. Now in this ammonia, we see that there are 2 lone pairs on the top, the 2 dots I made, and there are 3 bonded atoms. Sorry, my mistake here. It is 1 lone pair and only 1 lone pair and 3 bonded atoms. So let's look at the chart again, and here we see 1 lone pair and 3 bonded atoms is this shape, trigonal pyramid. So like a pyramid. So the base of the pyramid is these 3 hydrogens and the lone pair is on the top. So again, I'll show you this, but let's call it trigonal pyramidal, like a pyramid. which means the 3 hydrogens are at the base, the lone pair is on the top, and nitrogen is somewhere inside, like, where mummy is. Okay, the next is water, H2O. So let me get it in a different color. Okay, so here's the water, oxygen here, one hydrogen here, another hydrogen here, and you have these 2 dots on the side. That's the lone pair. So how many lone pair on the central atom? The central atom here is obviously oxygen. So we are going to write down here. So this is 2 lone pairs, and there are 2 bonded atoms. Okay, 2 lone pairs and 2 bonded atoms. So what does this relate to? 2 lone pairs and 2 bonded atoms is relating to 1 minute. 2 lone pairs and 2 bonded atoms right here is the internal. Yes, internally it's a tetrahedral, but externally it's a bent molecule. So from outside, it looks like a bent molecule in 3D. And the shape is 109 degrees Celsius of, the 2 hydrogens attached to oxygen. Okay, so that the shape is 109. So we will call this a bent shape. Bent. Okay, next look at HCHO. So let's get a different color here. So HC, so here are these 2 hydrogens, and here is carbon, and this is double bond. Okay, and fine, this oxygen has lone pairs and this oxygen has not. But what is the central atom here? The central atom is this carbon, is the central atom. And in this central atom, we will see that there is 3 bonded atoms. Remember that double bond with a double bonded oxygen is like 1 electron cloud. Carbon and hydrogen, 1 electron cloud. The other carbon and hydrogen is another electron cloud. So we see these are the 3 bonded atoms and 0 lone pair. So what does this correspond to? Let's go back and see. It corresponds to 3 bonded atoms and 0 lone pair. So it is trigonal planar, this one, trigonal planar. 3 bonded atoms and 0 lone pairs. So 3 bonded atoms and 0 lone pairs makes it trigonal planar. Okay, like a flat triangle, that's what it means. Okay, and we're going to go to the University of Colorado, the PhET site, and we're going to look at these molecular models. But for now, let's consider let's look at the shape of Pcl3. Now, Pcl3 has 2 lone pairs on the top, and the 3 chlorines are here on the side. Okay, so what does the shape look like here? So somewhat like, so it has got 1 lone pair on the central atom, and it's got 3 bonded atoms, and that shape equals to 1 lone pair and 3 bonded atoms is a trigonal pyramidal. Okay, so after some time, kind of remember it once you keep doing it, but for now it's okay to use this table as a reference. So trigonal pyramidal. All right, next is carbon dioxide. Now that one is really interesting, and let's get this green color here. Okay, so here is your carbon. These are the 2 oxygens, and we don't, the lone pair on the outer atoms doesn't matter. It's the lone pair on the central atom that defines the shape. Okay, and the bonded atoms, the shapes and their angles and all that. Now, what we see here is that carbon just by itself. So carbon has 0 lone pair and 2 bonded atoms. Okay, so let's go back and see. 0 lone pairs and 2 bonded atoms is a linear shape. This one right here. So 0 atoms, 0 lone pairs and 2 bonded atoms. So we covered everything that was on the table in these examples. So this is the linear shape. Okay, so this was using the table and determining the shape. Now, when we say the shape, so look at the angle, it's 180, it's like linear, it's like flat, like a stick. So this is one thing. So this whole thing is the VSEPR theory. Now, VSEPR, what does this mean? Valence shell electron pair repulsion theory. Okay, so this means that here's the thing, the lone pairs do not like the bonded atoms. Lone pairs, the non-bonded electrons, do not like bonded atoms. So what do? They push them. They keep them far away. So in the end, keep this in mind, when we talk about the electron groups here, what does this electron group mean? This means electron cloud. Now, these electron clouds are negatively charged. It's electrons. There is going to be repulsion. So when they repel each other, they try to push each other as far away in the region of space as is possible, still maintain the bond, the connectivity, still, but at the same time, they are as far away from each other. Keep this in mind that these negative electron clouds, are going to repel, and that can just throw away the molecule. Identity could be completely lost, and there couldn't be any stability. So in order to maintain the identity of the molecule, the best thing is for these bonded atoms and the lone pairs to spread out as far away. Now, on what you see on the screen is just in 2D, right? It's just a flat, when we draw these molecules here, these Lewis structures are just 2D structures, flat. But now I'm going to show you in a molecular modeling the 3D, how they look like. And then you can see how their angles, come into play and like how they push each other, okay? So just a minute here. Okay, so now we are at the site where the University of Colorado, they have placed very interesting simulations on a number of, concepts. So this is molecular modeling, where we see the 3D models of the molecules, the shapes of the molecules, we see their angles, we look at their molecular geometry, electron geometry, and the bond angles and so forth. So let's look at, on the screen you see is the BF3, which is boron trifluoride. So these yellow ones are, this is the fluorines. The middle one you see is the boron. Okay, so boron trifluoride. Now here, let's look at the bond angles first of all. You see, this is the best placement. Normally, when we draw things, we like to draw things at a 90 degrees. But 90 degrees is more constrained, and it's only in 2D. But in 3D, 180 is more, they are more spread out. So they are not knocking into each other, okay? So this is one thing. Next is, let's look at the molecular geometry. So molecular geometry is this, and the electron geometry is still trigonal planar, okay? Trigonal planar, and that means that, you see how this is flat. This is the real shape, like it's all very like plain, like it looks, right now it's looking linear, but in a flat, in a flat shape. So this is what it means. Okay, so that's the trigonal planar for BF3. Now let's look at for water. Now water, again, right now, I'm just showing you, let's show it with the lone pair. So these are the lone pairs in water molecule. Okay, the ones that you see like balloons. Okay, right here. You see that? These balloons, right? These two dots. So this is the real water molecule, okay? So the electron geometry tetrahedral. Tetrahedral is always like 4, and they are arranged, in like a chair, you can say, a 3-legged chair. So they are very far apart at 109 degree, all of them are. But if you look at the molecular geometry, let's remove the electron geometry now. Molecular geometry is bent. So when we say bent, these lone pairs, they push the bonded hydrogens down and far away, because here's the thing, bonded hydrogens are stuck right here. Okay, bonded hydrogens are like stuck to the oxygen, but the lone pairs have more freedom. So you see these lone pairs, these guys, they take the upper spot and they bend the bonded hydrogens. Okay, so anyways, that's for the water. Let's look at carbon dioxide now. This is carbon dioxide. Okay, bond angle 180. You see that? And the molecular geometry is linear. So no matter what, which side, you move them, they in the end they kind of just adjust, in that. So 180 degrees, where these oxygens are pushed that far away, that's the most optimum placement. So keep this in mind, that carbon oxygen, that double bond is one electron cloud. Carbon oxygen, double bond, another one is another electron cloud. So these electron clouds are going to bang into each other and just, repel. But in order to maintain that, that optimal distance from each other and still be connected to carbon, 180 degrees separation is the best for CO2 in the CO2 case. Okay, look at sulfur trioxide. Now, sulfur trioxide has a lone pair on top. And so these oxygens bonded, double bonded oxygens, lone pair on top, 119 degrees. So remember, lone pair again does not like bonded atoms. So they push them, further away from them, and they always take the top spot. So anyways, the molecular geometry is bent. And then let's look at ammonia. So this is how the ammonia looks like, the pyramid shape of ammonia. So these are the three hydrogens. And so right here, that's the pyramid shape. Looks like a pyramid, right? So, and then 107.8. So these hydrogens are 107.8 from each other also. So that's like equally, equal distance. And then the lone pair is on top. And then look at the uh, phosphorus phosphorus pentachloride. Phosphorus pentachloride. Phosphorus pentachloride has like 5 chlorines, which are these green ones. And as you can see, the angle, you know, is all of them are arranged at this angle, and the shape is trigonal bipyramidal. Now this is a bipyramid. So in this case means one pyramid on top of another. So this is an altogether different shape, this is an altogether different shape. And that's, we will look into this in our higher courses, but for my Chem 30A and Chem 007 courses, this is, or other introductory level chemistry courses, this is the tetrahedral shape of methane. Okay, so I'm going to leave it at that. This was a molecular modeling, idea to give you in 3D how they look like, but you're welcome to explore it. And I would really like to say thank you to University of Colorado for providing these offerings to us, specifically, in pandemic. I really have to say that it was very difficult to provide the meaningful laboratory experience to our students. So we really found the simulations that were available on this site to be very helpful. So I would like to say thank you for making this resource available to our students and to us, um, free of cost. Thank you. And with that, I would like to end this um, presentation. Thank you. Bye-bye.